Good morning and welcome to this lecture in our mechanical operations course. So the last two classes we have been talking about shape and size analysis. So we'll spend one more lecture hour talking about size analysis and then we'll move on to the next topic. So in the last class we covered aspects of dynamic analysis and static analysis of particles, particularly focusing on methods of collection of the particles and microscopic inspection and so on. And I mentioned that a way to measure the sizes of individual particles is by using light scattering characteristics, because those depend very sensitively on the properties of the particles. And so in terms of a quick and easy to operate method to measure particles of sizes of individual particles, scattering methods are very appropriate. Now when we again look at light scattering from a spherical particle, there is a scattering angle. So if the light is incident this way and the light is scattered this way, so this is I0 and this is I, this angle theta is referred to as the scattering angle. When theta tends to 0, it's called near forward scattering, and when theta tends to 180, that's called near backward scattering. And clearly the intensity of the transmitted or scattered light is highest when theta approaches 0. When we look at the scattering intensity, there are a couple of non-dimensional parameters that are very important. The first one, alpha, is defined as pi dp over lambda, where lambda is the wavelength of the incident radiation and dp is the diameter of the particle. When alpha is much smaller than 1, this is called the Rayleigh scattering regime. When it is of the order of 1, it is called the Mie scattering regime. And of course, when alpha is greater than 1, the particles are large enough that you are in the optical range. So essentially the laws of optics will start applying. But when alpha is much smaller than 1 or of the order of 1, then a different scattering regime is involved and different laws apply. In the range of alpha much smaller than 1, the scattered intensity I is proportional to I0 linearly. Higher the I0, the greater will be the I. It also depends on dp to the power 6, right? Depends on dp to the power 6. It depends on the distance between the source of the light to the particle that's being observed, and that dependence, like most force laws, goes as 1 over r squared, where r is the distance of separation from the light source to the particle that's being irradiated, and it also goes as 1 over lambda to the power 4, where lambda is the wavelength. The other non-dimensional parameter that's of relevance here is the refractive index. Now conventionally mu will be defined as c over Vp, where c is the velocity of light in vacuum and Vp is the velocity of light through the particle medium. There is also something called mu r, relative refractive index, which is defined as Vm over Vp. This is particularly relevant for particles that are suspended in a medium. So Vm is actually the velocity of light through the medium in which the particles are suspended, and Vp is again the velocity of light through the particle. And the scatter intensity, as it turns out, depends on a parameter that involves mu r. It's written as mu r squared minus 1 over mu r squared plus 2 the whole squared. So fairly complex dependence on the refractive index. And finally it depends on the scattering angle theta as 1 plus cos squared theta. So, these are the functional dependencies of the scattered light on the various parameters that are involved. So, you can imagine that you can, for example, measure theta or I as a function of theta, and it will have a certain relationship. Now, by measuring the intensity of the scattered light, what you are really trying to do is obviously calculate the particle size, right. Can you do that? In the Rayleigh scattering regime, it is actually possible to do that because you know everything else, I0, R, lambda, mu r, and you can measure the scattering intensity at various theta angles, or you can integrate over all thetas and get a total integrated value as well. So, you know all the other parameters, so you can estimate dP. So, that is a principle of measuring particle size through light scattering. Now, if you go to the regime of alpha being approximately equal to 1 or the Mie scattering regime, things are not so clear. The dependence of I on the various parameters is a little more nebulous. So, in the alpha approximately equal to 1 regime, I is still proportional to I0, it is still proportional to 1 over r squared, but and it is proportional to lambda squared. So, slightly different dependence on wavelength compared to the Rayleigh regime, but the most important difference in this case is that its dependence on dP is through something called a Mie scattering coefficient, and it is a fairly complex expression. So, if you plot I versus dP, we have seen before that I goes as 1 over dP to the power 6, but that dependence is not so obvious particularly in that Mie regime, which is a size range that is, if you actually look at this expression pi dP over lambda, again assuming that lambda is of the order of 0.6 to 0.8 microns, dP that is of the order of 0.1 to 0.5 microns. It is actually the most difficult particle size range to measure because of the fact that it happens to fall within this Mie regime, and in fact in the Mie regime, if you look at the dependence of I versus dP, it almost has a cyclical behavior. So, it is very difficult by measuring I to estimate what dP is, because the same I value can correspond to multiple dP values. Okay, so, that is a huge challenge, and of course, if you go even smaller than the Rayleigh regime, this itself we are talking about submicron particles, but if your particles are much smaller than that, again as we mentioned last time, the one big problem is you will not get much signal because it will drop as dP to the power 6. So, even though you are still in the Rayleigh regime, and theoretically it should be possible to estimate size based on the scattering intensity, because the scattered intensity is so low, it is hard to even measure it accurately. So, what do you do in that case? So, what the technique that people use is, if your particles are so small that they are below the Rayleigh scattering regime, that is typically in the nano dimensions, the only way to measure them through light scattering techniques is to grow them to a larger size and then measure them. So, there are techniques that are used in instruments called condensation nuclei counters or CNCs, where you actually intentionally condense a liquid on top of the particle until it grows to a large enough dimension where it can be measured using light scattering techniques. And then you correlate the measured sizes to the sizes that would have existed before you started condensing the vapor. So, you have to do some calibration initially to understand this relationship between what is the measured size versus what is the actual size, but once you have done that exercise once, provided you can control the process of this condensation precisely, you can always take particles that are sub Rayleigh regime, grow them to the Rayleigh regime, and then use light scattering as a way to measure particle size. However, you do not want to grow them too large, because as we have seen, once you exceed the Rayleigh regime and you get into the mean scattering regime, once again size determination becomes difficult, and you have to go even larger into the optical regime for you to again start measuring particle sizes with some level of confidence. Okay. So, size measurement, even though it is fairly easy in the larger sizes, in fact some of the methods you will be doing in the mechanical operations lab like sieving and sedimentation and so on are very good methods for particle size measurement, but for particles that are larger than about 40 microns. The challenges really are there when you try to measure particles that are finer, and light scattering is certainly a great technique to use, but you have to interpret the data carefully and you have to use some tricks once in a while to get particles to be in the right size range for you to be able to measure them accurately. Now, so what we have been talking about so far is measuring sizes of individual particles, but in reality in nature or manufacturing processes you very rarely have particles of a single size unless they are specifically manufactured that way for some purpose. So, the kind of particle size distribution you see is what we call polydisperse. In other words, there are a variety of particle sizes that can extend all the way from nanometers to millimeters, covering a very wide size range. So, you want to be able to detect particles that are not only in a certain size, but particles over a fairly wide size range. In order to do that, we have to use what are known as I was mentioning at the end of the class last time, particle counters and particle size analyzers. The difference between a particle counter and a particle size analyzer, a size analyzer is a simpler instrument. It does not give you counts, it does not tell you how many particles are between various size ranges. What it gives you is the mean statistic, what is the average size of the particles in the suspension, what is the standard deviation and so on. But it can measure down to very fine sizes, nano sizes, even up down to a tenth of a nanometer. But the price you pay is that you cannot count. A particle counter on the other hand gives you both counts and sizes. So, it will basically give you a tabular output that says, you know, for sizes within this range, these are the number of particles per ml of solution. For particles within this size range, this is the number of particles per ml. Okay. So, it does both, it gives you count as well as size, but the limitation of the method is because of the way it does the counting and sizing, you really cannot go down to nano dimensions. So, if you want to use a particle counter for nano suspensions, you really have to have a way again of growing the particles to a larger size and then measuring them. Of course, with nano suspensions, if you wait long enough, they will become larger just because of natural agglomeration tendencies, right. But the size enlargement has to be done in a controlled manner if you want to be able to back calculate the original size before the agglomeration happens. So, you cannot let uncontrolled agglomeration happen and then try to estimate the sizes of the original particle population. So, particle counters are very important because particle size distributions are polydispersed. For example, if you look at particles in the atmosphere, it does not matter where you do the measurement, pretty much anywhere on earth, I do not know about other planets, but anywhere on earth, if you measure particle size versus number of particles in that size range, and let us say you measure this from nanometers to micrometers to millimeters. So, suppose you just went outside and with a air particle counter and just sample the particles in the air. What type of distribution do you expect? Do you think it will be a normal distribution with a peak around some value, or do you think it will be a completely random distribution? Any idea? What we see is what is known as a trimodal distribution. This is for outside air. And the phenomena that contribute to this distribution is in the finest size range, it is nucleation, in the next size it is growth, and in the largest size this could be things like abrasion, dust, particulate emissions and so on. So, what happens is in the finest size range the first particles form because vapors condense and form very, very fine nuclei, right, and these nuclei are the first suspended particles that appear in the environment. Then what happens? The nucleated droplets or very fine solid particles start to find each other and slowly start agglomerating, and that is called the growth phase, and that is how we move from the nano dimensions to the micron dimensions. The third characteristic particle type is actually not really related to the first two, although it is possible that the growth can happen all the way from here to here, but it is more likely that an agglomerate once it gets to this size range will break up again, because agglomeration is not a irreversible process, it is a reversible process. So typically the particles in the largest size range come from a completely different source, just dust that has been entrained, or any type of automotive emissions or factory emissions, or simple processes of construction and so on, which can generate particles that are of a very different size range than what is naturally occurring. So in outside air you see a very wide distribution of particle sizes and you see this trimodal behavior. Now supposing you try to reproduce the same characteristic in indoor, for example in this room, if you did a particle size analysis, what do you think you will find? Interestingly enough, it is also trimodal. So you see a very, very similar behavior, but the sources are very different. In this case the finest particles appear not so much by nucleation, but rather by what is known as outgassing and condensation. The second phase is still growth, and the third phase again happens predominantly due to abrasive mechanisms which generate particles from surfaces. So the first peak is the one that is distinctly different for an indoor environment compared to an outdoor environment, and because what happens here, outgassing is a phenomenon by which any solid material naturally is constantly emitting vapors. The amount of vapors that are emitted may be very, very small, but it is happening, particularly polymers. Any plastic material will outgas small quantities all the time. Metals less, but certainly non-metals will outgas to a significant extent. So these vapors can recondense and form small nuclei. So that is the mechanism of formation of the finest particles in an indoor environment, which can then again agglomerate, and again the third peak could be due to completely different sources. Human beings, for example, we are a major source of particles, particularly in an indoor environment, contained environment like this. Okay? But the point is that when you look at naturally occurring particles, clearly there is a size distribution, and you have to be able to measure sizes then across this entire range. So whatever particle counter you use should either be optimized for measuring in a certain size. So for example, you might choose to use a particle counter here, a different particle counter here, and maybe some optical system to measure the larger sizes, and then you kind of put all the data together to get the full description. The difficulty with that is that different methods of particle size measurement are not easily correlatable. So you might see significant discontinuities between these three types of measurement when you actually plot and examine the data. So particle counters are very important instruments in many mechanical processing industries, particulate processing industries, both in the low tech as well as the high tech arena. For example, if you are manufacturing semiconductors in a clean room, you are very concerned about the distribution of particles inside the clean room, because these are the particles that would tend to deposit on your surfaces and cause device failures, yield losses, reliability issues. So there is a high amount of care and concern about airborne contaminants, both particulate as well as chemical, in the manufacturing environment of such high reliability devices. But at the same time, these particle counts are also important in for example cement manufacturing, because there it is more of a health and hygiene issue. You want to know the size distribution and concentration of particles in the machining environment, because humans can ingest these and that can cause adverse effects, some of them can be toxic. And so in both cases you are interested in knowing not only the nature of the particles that are being generated, but also the size distribution of the particles that are being generated. So particle counters are very, very useful instruments, and they have to satisfy certain requirements, and there is an acronym that you might want to remember, which summarizes the key characteristics of a particle counter: APRL, DS, or U. A stands for accuracy. Accuracy is a measure of how close to reality your reading is. Okay? So it is a measure of how well the instrument is able to replicate the real size of the particle. How do you determine accuracy? By using another technique and comparing. So the other technique that you use could be simply microscopic inspection, or it could be electron microscopy or whatever. So an independent method, and then you compare that reading to the reading for your particle counter. That gives you a measure of how accurate the reading is. Precision, on the other hand, measures something different. Precision is an indicator of how meaningful or small increments that you see in your data. For example, if you measure one particle as 1.2 micrometers and you measure the next particle as 1.3 micrometers, is that 0.1 micron real, or is that in the noise of the instrument? So precision is a measure of how well constructed the machine is, how good are the design aspects of the particle counter that you can rely on the data. If it says that there is a 0.01 micron differential between the sizes of these two particles, I believe it. So it's a measure of the confidence level that the observer has in the data that are being generated by the particle counter. R stands for two things: repeatability and reproducibility. The difference between the two is repeatability refers to an operator making two consecutive measurements on a sample and getting the same results every time. Okay? Repeatability involves one operator, multiple measurements on the same sample, and how close the readings are. Reproducibility, on the other hand, involves two operators who are measuring the same sample and how close their readings are. So they measure two different things. Repeatability is a measure of the robustness of the measurement method itself. Reproducibility is a measure of how well do two people doing the same measurement correlate with each other. Together, repeatability and reproducibility errors, if you add them, that is called the gauge capability of the instrument. The gauge capability of an instrument is a measure of, is a sum of its repeatability and its reproducibility. So it is not just a metric for the instrument, it is actually also an indicator of the procedure, because a procedure is really what drives particularly reproducibility. The procedure for the measurement has to be well enough defined, and it has to be clear enough that two people can follow the procedure and get the same reading. Whereas repeatability is a better measure of the instrument itself, because it is the same operator. So you have kind of taken the human element out of it, and you are asking the same operator to do two measurements and report the data. So that is more a measurement of how good the equipment is, and so together they give you a very good indication of how reliable the entire process is involving the procedure as well as the equipment. L stands for linearity. So let us say that you are measuring these parameters: accuracy, precision, reproducibility, repeatability over a wide range of sizes. How linear are the data? In other words, do you see a significant change in the slope when you go from one size range to another size range? you do not want that typically. You want these data to be linear with respect to particle counts, for example. In other words, as let us say the particle count is 100 in a particular size range, and you get a certain value for repeatability and reproducibility. Let us say that now the particle count increases to 1000. You do not want the repeatability and reproducibility to be very different, right. You do not want it to scale exactly proportionately. If the particle counts go up by 10, you do not want precision to go up by 10 times. What you are looking for is no abrupt changes. You want something that is not discontinuous. Okay. In fact, particle counts tend to be more repeatable and reproducible when there are more particles to count. As the sample becomes more and more dilute, actually the errors in the measurement can increase. And so your instrument has to be carefully designed so that this deterioration in repeatability and reproducibility as the number of particles decreases is not so much that the data become useless. Okay. So linearity is an important parameter to keep your eye on. D stands for dynamic range. That is basically the size range in which you are doing the measurement. The wider the size range, obviously the more useful the instrument is. You can take many different samples and run them through the same instrument, but there are many well constructed instruments that are really only good in a very narrow size range, could be from 0.1 nanometers to 10 nanometers. But as long as the instrument is doing its job well in that size range, that is okay. But you have to understand the size range in which the readings are reliable, and that is called the dynamic range of measurement. S stands for sensitivity. Sensitivity is a measure of the smallest size a particle counter can measure. The next one, R, is resolution, which is different from sensitivity. Resolution, I think we talked about this in one of the earlier lectures. Resolution is a measure of how close can two particles be and still be identified as being two discrete particles rather than a single agglomerate. Okay. So resolution has a lot of influence on how concentrated a sample can be, and you would still be able to measure it. An instrument that has poor resolution can only handle very dilute samples where there is a large distance of separation between adjacent particles. And finally, U stands for uniformity. Any sample that you measure, it is a sampling technique, right. So you are not really measuring the entire volume of material. So whether it is a airborne particle counter or whether it is a liquid particle counter, you are typically only measuring less than 1% of the volume that is available, and you are drawing conclusions based on that. So a critical requirement is that small sample that you take must be a fairly good representation of the whole, and the only way you can assure that is by making certain that the sample is uniform. How do you do that? Well, for example, with liquids, use stirring. It is a simple way to make particles distribution uniform, or you can use more sophisticated techniques involving high frequency vibrations and so on. In terms of an air sample, we kind of talked about this a little bit yesterday. There is no easy way. If you have a highly non-uniform sample, there is no easy way to make it uniform. So the entire facility has to be designed in such a way that the airflow inside the room is uniform, so that even a small sample of it can be considered representative of the entire facility. So these are the 8 primary characteristics of a particle counter that you must examine before choosing the instrument for your application. How do you ensure that all these aspects are covered? There are 2 processes, one is called calibration and the other is called correlation, that are necessary before you can start using a particle counter. Calibration refers to comparing your instrument against a traceable standard. In the US, there is something called NBS, National Bureau of Standards. In India, there is something called NIST, National Institute for Standards and Technologies. and these are bodies that are charged with housing calibration samples. So, if you want to calibrate a sensor that you are using for particle counting, there will be a standard that you have to compare to. Now, it is called a gold standard. So, calibration is done against a gold standard, which is typically an external standard that is maintained by a standards laboratory. Correlation, on the other hand, is done between what are known as silver standards. For example, a company that is doing, let us say, manufacturing of semiconductor wafers will have one development facility, it will have multiple manufacturing facility. So, the development facility will have a particle counter, and so will all the different manufacturing facilities. The particle counter at the development facility will be calibrated against an external standard, and once the calibration is done, that will be established as a silver standard. So, all the manufacturing facilities do not have to do their calibration against the gold standard. Instead, they can simply compare their readings to the readings that you are getting from the reference particle counter that is set up at the development facility. So, it essentially becomes what you call a silver standard. It is a substitute for a gold standard, simplifies the procedure for doing size measurements, particularly because calibration can take a while. You have to send your sensor back, you have to wait for it to be calibrated by the central standards lab and sent back to you, and manufacturing locations cannot afford to do that because typically you are doing 24/7. And so, the silver correlation actually works quite well in that particular context. So, let us say that you have calibrated and correlated your particle counters and you are doing all these measurements. Typically, the data that comes out of a particle counter will either be in a tabular form or it will be in a graphical form. In the tabular form, the typical template that of the data would look like this. So, there will be a channel number, size range, and differential counts. So, for example, in a particle counter channel 1, we have a size range from 0.1 microns to 0.2 microns, and you may get about 1,000 particles in this size range per unit volume of the material that you are sampling. The differential count is the count that is obtained in that channel. So, it is the number of particles that are sized between 0.1 to 0.2 microns. And similarly, there will be a channel 2, let us say 0.2 to 0.5, maybe 500 particles, channel 3 maybe 0.5 to 1, maybe 200 particles, 1 to 5, maybe 50 particles, and 5 which may be greater than 5, and there may be 0 particles. So, this is a sample whose particles are all in a size range between 0.1 microns to 5 microns, and there are no particles that are larger than 5 microns. Now, this data can also be represented as cumulative counts. So, you just count backwards. So, the number of particles that are larger than 1 micron would be 50, larger than 0.5 microns would be 250, larger than 0.2 microns would be 750, and larger than 0.1 microns will be 1750. Why do we want to represent data both ways? Because differential counts are of relevance to certain industries and cumulative counts are of relevance to other industries. For example, again, if you are running a factory that is making semiconductor wafers, you are interested in the cumulative counts because you want to know how many total particles there are in your system larger than various sizes. And the reason for that is for every device, electronic device, there is a certain size that is a threshold size above which particles can harm your product, but below which they will have no effect. And so you want to know particularly for your product with a certain threshold size how many particles there are in the environment that are larger than that size, because those are the particles I am going to worry about. I am not going to worry about particles that are finer than that. On the other hand, there may be applications where a product has a certain sensitivity in a particular size range. It may not be sensitive to particles that are larger, and it may not be sensitive to particles that are smaller, but there is this window of particle sizes where there is extreme sensitivity of the device, in which case you would want to know the differential count in that particular size range. In fact, there are even cases where the inverse can be true. For example, with many of the human health and hygiene kind of things, you do not really care about particles that are larger than a certain size, but mainly about particles that are smaller than a certain size. The reason for that is, larger particles will get filtered out by our nose. We have very effective filters in our, when we breathe in, which can trap large particles quite well, but particles that are smaller than a certain size can make it through and enter your body. And so, and similarly your skin also, your skin pore size, larger things are kept out, but if you have very fine vapors or particles, they can actually penetrate through the skin. So in that case, you will be mostly worried about particles that are smaller than a certain size. So this type of tabulation of data is very crucial in order for us to capture all these different parameters for different applications. And you can certainly graph the data different ways also. You can graph it as differential counts, you can graph it as cumulative counts, depending on your needs. The other thing that you can derive from these are mean diameters. When you have a particle distribution, while sometimes you may be interested in the actual distribution by particle size, sometimes you may only want to know the mean size and the standard deviation in the size. In that case, you have to be able to calculate the means based on the tabulated data. There is no unique mean. There are various mean sizes that you can define which represent various moments of the data. So for example, you can talk about a number mean diameter, which would be simply summation ni di over summation ni, where di may be an average size within a size channel. So in this size channel 0.15 may be a representative diameter, and ni would be the number of particles in that size range as well. You can also talk about a diameter mean diameter, which is summation ni di over summation ni di. You can talk about a area mean diameter, which is same thing, di squared. A volume mean diameter, same thing, di cubed. You can talk about a mass mean diameter. If particles in different size ranges happen to have different densities, you also have to include that. So it will be this times rho I di cubed. And you can talk about a scattering mean diameter, which will be di to the power 6, and so on. So by taking various moments of the particle size distribution, you can define various mean sizes. So how do you choose which one you use? Depends on your application. Again, if your product is susceptible to number of particles, then the number mean may be the most relevant for you. On the other hand, if you have an application like catalysis, where the average size, the average area is the most important parameter for you, then the area mean diameter may be the most important. If you have an application where you are trying to look at scattering, then the scattering mean diameter may be the most relevant. So you have to choose from these means based on the application at hand. And these means can be quite different for different particles, for different distributions, particularly if it is not a normal distribution. There are three types of particle size distributions: normal, log normal, and power law. Between the three, they pretty much encapsulate all the different particle size distributions that we see in nature. So, particles that are so the difference between them, the normal distribution, although the name says normal, is actually the least likely to occur in nature. Log normal distributions are probably the most likely to occur in nature, and a power law distribution happens when you have an environment where particle counts are artificially controlled for some reason. Now, I think that these types of particle size distributions occur in many types of mechanical operations. For example, milling and grinding produce a certain size distribution which follows a certain pattern, whereas if you are doing filtration, you are likely to come up with a particle size distribution that is very different. I think it is worth spending a little bit of time on this, and since we are running out of time for this lecture, I will postpone this discussion to the next lecture. Okay. Any questions on what we have covered so far? Yeah.
Process of outgassing.
So, process of outgassing. Any material is constantly emitting a vapor. If you had a sensitive enough instrument, I could put it around you and you will see that you are constantly emitting vapors. Just like we are all emitting particles. If I bring a particle counter near any of us and measure, we are constantly shedding. Our skin is shedding, our clothes are shedding. So, all human beings are a constant source of various types of particulate and chemical contamination, as are virtually any material that you have in a room. The only way to prevent outgassing, for example, the screen is right now outgassing material. It may be picogram level or it may be microgram levels. The only way to prevent that from happening is to there is a process called vacuum baking, where you can take this and really bake out anything that can come out of it before you install it. Then you can virtually eliminate the outgassing, but even then there is also constantly a process of condensation happening, because all the stuff that is in the environment is constantly condensing, and that again starts to outgas. So, outgassing is never preventable, can be reduced, and by the way, outgassing increases as temperature increases. So, in a hotter environment there is more outgassing. Okay, so let me talk about the next few classes. I think again Thursday afternoon 1 p.m. I kind of want to use as your study time. So, we will do that this week also. Next week I think Monday is a non-instructional day for Shastra. Has that been announced? And Tuesday is a holiday. And Wednesday I am unfortunately going to Singapore. I won't be here Wednesday and Thursday. So, what I am going to suggest is the lectures that the last 3 lectures are actually, the material is contained in about 10 lectures in my particle characterization course. So, use this time to go through all the 10 lectures. So, this will be lectures 3 through 12, okay. And so, by the time you come back Monday after next, I want you to be pretty much clear on size and shape characterization in all its aspects. And like I said, I would like to start with 2 things. One is I will finish up this discussion on particle size distribution, because that is important as it relates to mechanical operations, and we may do a quick pop quiz just to make sure that you have listened to the lectures and you have kind of grasped the concepts. You do not need to do any memorization. It will be based on what I would think of as concepts that you need to extract from the material relating to size and shape analysis, and then we will cover, there are a few more fundamental aspects of particles that we need to understand before we start talking about specific mechanical operations. For example, particle dynamics, how do particles move around in various environments, particle adhesion and cohesion, how do particles stick to each other, how do they stick to surfaces, particle transport characteristics in general. And once we have covered that, I think we would have covered most of the basics that are going to be common to all the different modules that are in the mechanical operations course, and then we will start talking about the specific modules in mechanical operations. Okay? So, I guess I will see you Monday after next. But you are welcome to stop by and talk to me anytime if you have any doubts on any of the materials. All right, see you then.